The transverse shear stress acting in a beam of rectangular cross-section subjected to a transverse shear load is. They have said about a beam of rectangular cross-section which is loaded transversely. That is, a transverse shear load is loaded. So you will be eventually getting a transverse shear stress acting on that beam. And they have particularly asked regarding rectangular cross-section. Remember that. They have asked the variation of the transverse shear stress. And you can see that it is evident from the options. Here you can see that it is a variable with maximum at the bottom of the beam, variable with maximum at the top of the beam, uniform, variable with maximum on the neutral axis. So it is clear that they have asked regarding the transverse shear stress variation in a beam of rectangular cross section. We must remember that always transverse shear stress varies parabolically from fiber to fiber. Here you can see from bottom fiber to top fiber, the shear stress varies parabolically. This is a generic line for which matches for all kinds of cross section, but this parabolic variation will not be the same in all cases. It will be parabolically varying, but it will be of different shapes. For rectangle, this is the particular shape. For particularly rectangle, this is the shape, and you can see that the maximum transverse shear stress occurs at the neutral axis of a rectangle, which occurs at the mid depth. So tau max is calculated as 3 by 2 tau average. It is derived using certain formulae and conditions. You just remember this term and you should remember what is tau average. Tau average refers to shear force at that cross section divided by the cross sectional area. Here it is a rectangle, so it is F divided by F refers to the shear force and divided by the area. Area can be written as B into H, breadth into height. So 3 by 2 F by BH will be the maximum shear stress acting on the neutral axis. So it is clear that the variable with maximum on the neutral axis corresponds to the transverse shear stress variation in the case of a rectangular beam subjected to a transverse shear load. An axial residual compressive stress due to a manufacturing process is present on the outer surface of a rotating shaft subjected to bending. Always remember, when a rotating shaft is subjected to bending, it becomes a fatigue loading condition. So they have mentioned fatigue life here. Here you can see, let's read the question further. Under a given bending load, the fatigue life of the shaft in the presence of residual compressive stress is. They have asked the impact of residual compressive stress on the fatigue life of the shaft. Okay, here are the options as decreased, increased or decreased depending on the external bending load, and neither decreased nor increased, and finally increased. It is a 2008 GATE 1 mark question. Remember that whenever a rotating shaft is subjected to bending, it comes under fatigue loading condition. Why? It is because when a rotating shaft is subjected to bending, due to bending, it will be having tensile stress and compressive stress on either top or at the bottom. Both will be acting. One will be at the top and the other will be at the bottom, or vice versa. In such a case, due to rotation, the fibers get changed with the position. As a result, the tensile stress will become compressive stress. So, a particular fiber, when it is at the top, it will be subjected to tensile load, and when it comes down due to rotation, half rotation, it will be subjected to compressive stress. So there is a variation of load. This kind of cyclic loading is called fatigue loading, and it is experimentally determined that fatigue failures do not occur when the mean stress is compressive in nature. This particular statement you can understand when you go through design concepts of Soderberg equation, Goodman equation. Okay. Fatigue life can be improved by inducing compressive stress on the surface of material. This is a well-known fact in the case of manufacturing technology. So you must remember that fatigue life always get increased by inducing a compressive stress on the surface of material. So axial residual compressive stress is a positive phenomenon. So it gets increased is the right answer. For the component loaded with a force F, as shown in the figure, the axial stress at the corner point P is. They have asked the axial stress at this particular point, and they have given the diagram as shown here. And these are the options. It is a 2008 GATE 2 mark question, but it is simply based on the basics of engineering mechanics. Since it is loaded at an eccentricity, you can replace this load. That is, at this point, you have to replace it with a force and a couple. which we would have studied in our engineering mechanics concept, that a force which is loaded at a distance from a particular point can be replaced with a force at a couple at that particular point. So just by replacing this with force and couple, you will be getting an axial load F and a momentum, which is actually a couple F into L minus B. The reason for stating it as a couple is F, you should be considering here another load acting in opposite direction, and at the same time an equivalent load acting in the same direction as that of F. So two will be cancelled. You should imagine that in such a case you will be getting a straight axial load, and at the same time this downward load and this imaginary upward load will be causing a couple, resulting in a moment of F into L minus B. So you are getting, due to eccentric loading, point P experiences both axial load and a bending couple of F into L minus B. And we know that axial stress is calculated as F by area. That is, this area is given as 2B into 2B. So it is F by 2B the whole square. We also know that bending stress is calculated as M by I is equal to sigma B by Y, which gives M Y by I is equal to sigma B. Here you know F into L minus B becomes the moment, which is M, and Y refers to the distance of the which is the maximum distance of the outermost fiber. Here B comes out to be the maximum distance from the neutral axis. You will be getting B, and we also know that for a square cross section, since it is 2B cross 2B, for a square cross section, I is given as 2B whole power 4 by 12. So just by solving this, you will be getting D as the answer. A frame of two arms of equal length L is shown in the adjacent figure. The flexural rigidity of each arm of the frame is EI. Flexural rigidity is always given as EI. E refers to Young's modulus and I refers to the moment of inertia. The vertical deflection at the point of application of load P is, they have asked vertical deflection at this point. It is a 2009 GATE 2-mark question. Okay, here we are applying the Castigliano's theorem. The reason for applying Castigliano's theorem is it is simpler in this particular condition where vertical deflection at the point of application of concentrated point load is asked. If it is asked in such a way, Castigliano's theorem is easier. But if it is asked as slope at the point of application of the concentrated point load, then it is not easier. So whenever vertical deflection at point of application of concentrated point load is asked, Castigliano's theorem becomes simpler. Similarly, when a moment acts and the slope at the point of application of moment is asked, Castigliano's theorem becomes easier. It is given as deflection at a point A where the load is applied is equal to differential of the strain energy with respect to the load acting. Here load acting is, I have referred as W, but here it is P, so I have replaced it with dou U by dou PA. Here we have to find the strain energy of the whole frame. So we are splitting it into two frames and we are finding the reactions. Here you can see the free body diagrams. Try revising the engineering mechanics concept and understand the reactions, and based on those reactions we will be finding the moment here. First, let us know the horizontal member's strain energy. It is given as mx squared dx by 2ei. This refers to integral. So it is integrated from 0 to L minus px. Why it is minus px? Because p is applied and at a distance x, the moment will be minus px since it is acting downwards. So minus px whole square into dx by 2ei, 0 to L. Upon integrating, you will be getting a particular value. And similarly, for a vertical member, you are integrating from 0 to L, the moment whole square into dx by 2ei. You will be getting a strain energy value for this particular vertical member. So you must add both and you will be getting the total strain energy of the whole frame. And here you can see the total strain energy is given as P squared L cube by 3ei. This P squared L cube 3ei is differentiated with respect to the load P. So you'll be getting 2P L cube by 3ei. Always remember, when a vertical member or a horizontal member is subjected to TSL, there will be a moment, and that moment is responsible for the strain energy. So you are calculating the summation of the both strain energies and you are using Castigliano's theorem, and finally you are getting the deflection at the point of application of the concentrated point load. Linked data questions 5 and 6. A massless beam has a loading pattern as shown in the figure. The beam is of rectangular cross section with a width of 30 mm and a height of 100 mm. And this diagram and this data belongs to both 5th and 6th question. They have asked the maximum bending moment occurring point, and they have given different locations. It is a 2010 gate 2-mark question. I haven't given the free body diagram. This is because you people have to make the free body diagram and determine the reactions. You will be getting RA to be 1500 Newton and RC to be 4500 Newton. And now let us determine the bending moment equation from B to C, because since the loading is different from A to B and B to C, we are determining the bending moment equation for this particular B to C section. So if you consider cross section from C at a distance x, you can find that this RC into that x. So RC is 4500. So 4500 into x, you are considering it as a positive moment, minus due to this uniform load up to this x, you have to multiply into 3000. So 3000 into x will be the load which will be at a distance x by 2 from C. So 3000 x into x by 2. So this is the actual bending moment equation for this particular portion of the beam. So by differentiating and equating to 0, you will be getting the maximum bending moment occurring point. Here it comes out to be 1.5. So from x it is 1.5. So from C it is 1.5 means it comes at this point, which is 2500 mm. So keep this and substitute this 1.5. You will be getting moment to be 3375. Why we are calculating this? Just by seeing this, you can answer 2500. But remember, if the reaction here is maximum, then this will cause a maximum bending moment at this point. So you must consider this loading also. Just by multiplying the reaction, that is 1500 into 2, you will be getting 3000 Newton meter. So 3375 is the maximum Newton meter, that is a maximum bending moment. So x is equal to 1.5 is the point where maximum stress is happening. If it is 1.5 from the right hand side, then it is 2.5 from the left hand side, that is 2500 mm to the right of A. So C comes out to be the answer. Another way of solving this is find the shear force at a distance x from A. From A, determine the shear force equation, and maximum bending moment occurs where shear force is 0. Just by equating that shear force equation to 0, you can get the maximum bending moment occurring point, and this method of solving is explained in most of the books. So consider both the options and try solving using this, and try drawing free body diagram and solving this. The maximum magnitude of bending stress in megapascal is given by. They have asked the maximum magnitude of bending stress. We have calculated the maximum bending moment in the previous question linked to this question, and they have given different magnitudes as the answer. It is also a 2-mark question. Okay, here you can see, as we know, the maximum bending moment which we have calculated from the previous question as 3375 Newton meter, and we also know that sigma B max by Y is equal to M max by ZNA. Since it is a symmetric cross section, that is a rectangular cross section, it is given as sigma B max is equal to M max by ZNA. ZNA is equal to I by Y. So Y when goes up, it will become Y by I, so it is ZNA. The section modulus of the neutral axis is given as BH squared by 6. 3375 divided by BH squared by 6. Just by substituting the values, you will be getting the maximum magnitude of bending stress as 67.5 megapascal. Linked data questions 7 and 8. A triangular shaped cantilever beam of uniform thickness is shown in the figure. They have stated that it is of uniform thickness. The Young's modulus of the material of the beam is E. A concentrated load P is applied at the free end of the beam. Okay. They have asked the area moment of inertia about the neutral axis of a cross section at a distance x measured from the free end. You can see that if a cross section, that is just by bisection, you can see that you will be getting a rectangular cross section. It is a 2011 gate 2 marks question, and you have given different options. By using similar triangle concept, we can determine the breadth at a distance x from free end, because breadth is the variable one while the thickness remains the same as given in the question. So by similar triangle concept, x divided by the total length is equal to b dash. B dash is the breadth at a distance x from free end. So b dash divided by b. So b dash is given as xb by L. We know that since it is a rectangular cross section, when you cut it transversely, you will be getting a rectangular cross section. The moment of inertia about the neutral axis is given as bh cube by 12. We know that here we must substitute b dash. It is a generalized formula. Here we are calculating at this cross section at a distance x. Here it is given as b dash. So instead of b dash, if you substitute, it will be xb by L. So xb by 12L, while h is t. So it becomes xb t cube by 12L. So B is the right answer. The maximum deflection of the beam is, the given beam is a cantilever beam and they have asked the maximum deflection. It is also a 2-mark question. Always remember that for a cantilever, deflection is maximum at the free end only. Always the deflection and also the slope will always be maximum at the free end only. Here also we are using the Castigliano's theorem because it is simpler to use. As I have stated earlier, the load is acting at the free end and deflection is asked at the free end. So whenever deflection is asked at a point where concentrated point load is acting, then Castigliano's theorem becomes simpler. So here we are calculating the strain energy as I stated earlier, due to the transverse shear load, there will be bending, which will be P into X. So minus Px whole squared into dx by 2EA. We are differentiating from to go the length of the beam. So it is 0 to L. You will be getting 6P squared L by EBT cube into how it becomes EBT cube. We have calculated INA in the previous question. Just by substituting here, you will be getting 0 to L x into dx. You will be getting finally the strain energy to be this. And according to Castigliano's theorem, we have to differentiate with respect to the load. So you'll be getting 3 into 2, 6 PL cube by EBT cube. So D is the right answer. Consider a cantilever beam having negligible mass, that is the mass is neglected, and a uniform flexural rigidity, that is a constant E into I, with length 0.01 meter. The frequency of vibration of the beam with a 0.5 kilogram mass attached at the free tip is 100 hertz. 0.5 kilogram means the force comes out to be 0.5 into 9.81 Newton. So the frequency is given as 100 hertz. That is, they have given the frequency in terms of per second. They have asked the flexural rigidity of the beam. It is a 2014 GATE set 1 question being asked for 2 marks. We must know that actually it is a natural frequency concept comes under vibrations in theory of machines. So these are some easy formula to be remembered. Natural frequency in terms of hertz is given as omega n by 2 pi. Omega n is referred to as natural frequency in radian per second, while Fn refers to natural frequency in hertz. Okay, this is the relation between a natural frequency in hertz and natural frequency in radian per second. Also, we must remember that natural frequency is always equal to root of S by M. That is, omega n is equal to root of S by M, where S is the stiffness given as load by deflection. For a cantilever beam, particularly having a point load at tip, the maximum deflection is given as PL cube by 3EI. You have to remember this formula. They have asked the EI, flexural rigidity of a beam. So by consolidating all these formulae and simplifying, you will be getting EI is equal to S into L cube by 3. So just by substituting the given values, you will be getting the flexural rigidity. You must remember what is natural frequency in terms of hertz and radian per second, and what is stiffness and the deflection formula for a cantilever being loaded at the tip. You can find easily the flexural rigidity. Okay, it is found to be 0.06573. The flexural rigidity of a cantilever beam is assumed to be constant over the length of the beam shown in figure. If a load P and bending moment PL by 2 are applied at the free end of the beam, then the value of the slope at the free end is. They have asked the slope at the free end, and it is a 2013 set to question being asked for 2 marks. Here you can see the different options given. Since it is a different kind of, that is 2 different kinds of loading, it is solved by using superposition principle. That is, it is a simple addition problem. Here you have to add the slope due to concentrated point load alone and the slope due to the moment alone. Here you can see theta is equal to theta 1 plus theta 2. Theta 1 is given as slope due to point load alone. Here I have demonstrated the cantilever beam with load alone, that is point load alone. Similarly for theta 2, slope due to moment, that is this particular couple alone. So it will be like this. So just by adding, you can get the final slope due to this kind of loading. Theta 1 is given as PL squared by 2EA. That is for a point loaded, that is a cantilever beam with the point load at the tip will be having a slope of PL squared by 2EA. Similarly, a cantilever beam with a moment PL by 2 at the tip will be having PL squared by 2EA. The general formula is ML by EA. So instead of M, you have to replace it with PL by 2. So you'll be getting PL squared by 2EA. Just by adding, you'll be getting PL squared by EA.